Hey everybody, this is Miss Segovia bringing you a screencast from home today. If you hear some weird noises in the background like birds chirping or a little boy talking, that's what it's from. So let me give you a brief introduction to momentum and work a couple practice problems with you. Momentum and impulse. Momentum is how hard is it to stop something and a product of an object's mass and its velocity. It's increased if either the mass or the velocity is increased. So you guys already kind of know momentum from common day language. You know, if something big is rolling at you and you try to stop it, it's not going to be easy. But if something tiny is rolling at you, it's a little bit simpler to stop because of the change in mass. Of course, it also depends upon how fast thing is going. A little tiny bullet going, a couple hundred miles an hour, that will be difficult to stop. Whereas if it's just rolling along at 5 meters, then you could probably bring it to a halt. So when we calculate momentum, the formula is pretty simple: mass times velocity. So if you look here, we've worked several examples for you. You've got a 2 kilogram box and it's going 3 meters per second, so 2 times 3 is 6. An 8 kilogram box moving 3 meters per second is 24. And it just kind of keeps going. If something's not moving, if it's 2 kilograms and its velocity is 3 meters per second, but in this case there's no vector arrow here, so it's actually come to a stop, it's got a momentum of 0. If something's moving in the opposite direction, so in this case it's moving to the left, the velocity is going to be negative, not because it's less than 0, but because it's left direction. Then our momentum will also be negative, -6, and our units of momentum is a little crazy. It's kilograms meters per second. So kgm over s, kind of a pain. We don't have a nice simple watts or joules to simplify it. It's just kgm per s. So remember that on your next test to give that full label for these. You don't have to memorize momentum. If you guys look at your formula charts, we have it. Right here, we got momentum is mass times velocity. In a little bit here, we're going to talk about impulse and even the law of conservation of momentum. So don't worry about trying to memorize these, just know how to use them when you see them. So let's go ahead and work a sample problem. Calculate the object's momentum at position A. So again, what's our formula for momentum? It is mass equals velocity. Oh, also you'll notice we use the letter P for momentum. It's because we use M already for mass, meters. We had to pick a new letter, and the only one that really seemed to make sense was P because nothing else really uses it except for power, but they use capital P. I don't know, I'm not a physicist. I wasn't there and they made that decision. Alright, so our mass of object A is 3 kilograms, so we're going to take 3 kilograms times our velocity, which is 5 meters per second, and multiply those together and you get 15. Again, the units, kilogram meter per second. 17 is asking us to calculate the delta V between positions A and B. So that's our change in velocity. So change of velocity between positions A and B, the velocity, or our formula here for that one, would be delta V equals our final velocity minus our initial velocity. And so our final velocity that it's going to end up at is 2 meters per second. Subtracting our initial velocity, which is 5 meters per second. So I don't know if you need a calculator for this one, but it should come out to be -3 meters per second. Again, you can kind of tell that because it's going to be slowing down a little bit, so we would have the negative there. And then they're asking us to calculate the delta P between positions B and D. So it's a bit of a mouthful, but delta P is just what's the change in momentum. So in order to find the change in momentum for B and D, we need to find out what were their momentums to begin with. So let's do the momentum for B. So our P value is mass times velocity. The mass of B is 3 kilograms. Its velocity is 2 meters per second. Multiply those two together and you get 6 kilogram meters per second. Sorry, it's a little sloppy looking. My pen's kind of dying on me here. Our D momentum, our mass of D is 3 kilograms. Its velocity is -4 meters per second. You can tell it's moving to the left, so that's where the negative comes from. And then that gives us -12 kilogram meters per second. So to calculate our delta P value, so anytime we do the change in something, we take the final minus the initial. And so our final velocity was negative 12. I'm just going to leave the label off for right now. It's kilogram meters per second, minus our initial velocity, which was 6 kilogram meters per second. And when we basically negative 12 minus 6 is going to be negative 18 kilogram meters per second. So that would be your change in momentum for objects B and D. The next thing you have to know is momentum is a vector. Being a vector, it has a magnitude and direction and must be treated like all vectors. It can have components and can be added or subtracted. So if you look in our first example over here, when we have momentum to the right, or vectors to the right, and competing one to the left, we're essentially going to add them together like they show up here. This one was 12, this is minus 4, so 12 minus 4 is 8. And so that's why we see here this vector is still going to the right. We have a positive value, so that's a right-leaning value. But it's 8, it's a little less because it was counteracted by the 4. These over here, this is kind of like your little nightmarish projectile motion again, where we have component vectors. This is the actual direction of our momentum right here. It's 12 kilogram meters per second. But since it's going at an angle, we have a horizontal value and we have a vertical value. In this case, it's going down. To do these, it's like we've done before with our sines and cosines. You would take we would call this basically our P naught, our initial momentum right here, and this is our x value and our y value of our momentum. When we calculate that to find our x components of that, we're going to take our hypotenuse, which is our P naught, cosine of theta. To find your vertical values, it's similar, but except we use sine theta, so P naught sine theta, just like we did with velocity vectors. Graphically to find the momentum, so if we flip to the other page, if you look at 24 and 25 on this one, on 24 you've got 3 vectors right here, and we want to find what's the net momentum. You basically just put them together, so you've got your P1 was going up, P2 is going down to the right, and P3 is traveling this way. We look at where do we start initially to where do we end up finally. It's a little tricky to draw here because they kind of end up one on top of the other, but your net vector is going to be this, from the start of the initial one right here to where it meets the final one. You just put it together like a little puzzle. On 25, we want to find the x and y components. So our px is going to be this one here, and then our py is our vertical component of our momentum. Now, they give us velocity and mass right here, but they don't give us the momentum in this direction. So we've got to calculate that one just using the basic momentum formula. So our momentum is mass times velocity. So we're going to take our 6 kilograms times our 4 meters per second that they gave us there, and you're going to get your 24 kilogram meters per second. And then using those formulas I showed you before, we can find the vertical component and horizontal component. So let's do the py value first. Our P naught value, our horizontal value from the hypotenuse, is 24 kilogram meters per second. And since we're going vertically, that means we need to use sine. So sine of our angle, which they gave us right here, is 42. So 24 kilogram meters per second times the sine of 42. You plug that into your calculator, you should get 16.1, and the unit is still kilogram meter per second. So that is your vertical component. To find your horizontal component, we have to use cosine. So 24 kilogram meter per second cosine of 42, and plug that one in and you should get 17.8 kilogram meter per second for your horizontal component. Again, if you forgot those formulas, just flip back. It's using SOHCAHTOA. I'm just shortening it up right now. Net momentum. Together, multiple objects can have a net momentum, and basically we just add them all together. If they're negative, we essentially subtract. So here in our first example, you've got your 6 kilogram per meter seconds going to the right. Sorry, it's such a long label. And then on the right hand side, since it's traveling to the left, it's negative 24 kilogram meters per second. And so we just add those together. So 6 plus a negative 24 is going to be negative 18. Like they showed you, much nicer than I'm writing up here. It is possible for net momentum to be 0. As you can see, this one's 18, this one's negative 18. Add those two together and you get 0 kilogram meters per second. So basically they're going to cancel each other out. So let's work an example one like that. Going back a little bit, calculate the P net of A and B above. So in order to do that, let's go ahead and calculate our individual momentums first. And so 6 times 5 is 30. I'm going to leave off the labels right now just for simplicity. 4 times 3 is 12. 1 times 0 is 0. And 6 times negative 2 is negative 12. So these are the momentums for all the boxes above, of course minus the labels. So if we want to do the net momentum of A and B above, to find the P net, you just add those two values. So A was 30 plus B is 12, so your net momentum of those two is 42 kilogram meters per second. The P net of B and D, well, B is 12, D is negative 12, so they're going to cancel each other out and get 0. So 0 kilogram meters per second. And then calculate the P net for all 4 objects. So we're going to take 30 plus 12 plus 0 minus 12 equals 30 kilogram meters per second. Isn't that nice? Simple, simple math. The other part of momentum is impulse, and impulse is a force acting over time. It's just like work. So we still have conservation of momentum problems just like we had in our conservation of energy problems. And so when we do these, our formula that we're going to use is impulse equals force times time. Now on your formula chart it looks a little bit different. They still give us force and change in time right here, so it almost looks like fat. Impulse equals fat, and we use the letter J for impulse because again we ran out of letters, and I looks like a stick and that confuses people. We can also use mass and change in velocity for a momentum as well, and you can see that relates back to our original momentum equation, mass times velocity, just here we're dealing with a change in velocity. So you could potentially see it either way. When we look at a sample problem here, we've got find the impulse on an object. So let's just use the force times time. So impulse equals force times the change in time. And so our force here is our 6 newtons. And our change in time is 10 seconds. So 6 times 10 seconds. Oop, don't need a calculator for that one either, do you? It is 60. Again, the units for this one are going to be kilogram meter per second, because the newtons, if you break that down, you get that value, so on and so forth. Just so you know that. The final momentum of the object in part B. Well, it's at rest. The Newton pulls on it to the right for 10 seconds. So if our impulse force here was 60, we started out at 0, so we get 0 plus our impulse of 60, and our final momentum is going to be 60 kilogram meters per second. And so then what's the final velocity? Well, to find our final velocity, we got to go back to our momentum equation, where momentum equals mass times velocity. Since we now know the momentum of the object is 60 kilogram meters per second, the mass of our object was given back in the problem at 20 kilograms. So, where'd it go? 20 kilograms times velocity. So if we divide both sides by our 20 kilograms, that one by 20 kilograms, 60 over 20, our final answer is going to be 30. Our kilograms cancel out. Meters per second equals our velocity. So that's just a quick little help on how to work momentum problems. Mr. Flint will be around to help you, and when I come back to school I'll be able to help you as well. But work through your packet, check the answer keys on the website and in the room, and I hope you have fun learning about momentum.